In this practice problems video, we're going to review the most common way to solve a differential equation, or the so-called the direct integration method, or you can call the DIM method. So what is the direct integration method? So let's learn how to find a differential equation. So we know that we find a derivative by taking the differentiation. So you take the differentiation to find the derivative. So that means to undo that, what we need to do is we integrate. So like a very simple idea. So we take the derivative we take the differentiation to find the derivative. To undo that, we can take the integral. And then how we do it? We use the common antiderivative table. So there are a lot of common tables that you need to remember for a differential equation class or any calculus like 2-3 classes. And then if you are not familiar with that, you can find the link in the description. So before you do any problems here, I would like to recommend that you go through that and try to memorize them or familiarize with those common antiderivatives tables, because those are very important when you want to solve a problem, because otherwise you're going to get too much time to solve a problem. So in the direct integration method, there are two types. So let's talk about those two types one by one. So let's talk about type 1. So type 1 means you have a differential equation. On the right side, you have a function which is the function of the independent variables. You can see this is a function of the independent variables. That's a type 1 independent variable. The independent variable in this case is x, and you can see it's a function of x. So if this is the case, this is so simple, because you know that you took this one, you got this one by taking a derivative of a certain function. So to undo that, what we're going to do, you take the integral with respect to the independent variable. So it's a very simple idea. So what we can do, by integrating with respect to x, by integrating with respect to x, because x is the independent variable, what will happen is, so you just take the integral of both sides. So this is the most basic case. And then also the other side, fx dx. And then what happened on the left side, you can see, so you start with the function, take the derivative, now you integrate it, that means you should get the function back. So that means the left side simply become y, the original starting function, and the other side you have fx dx. So that means this is a, and also I'm just going to exaggerate this one because there should be a constant. So that is the formula for the type 1. And you can see this is the most basic method of solving a differential equation. Just take the integral with respect to x. So let's look at some problems and just get familiarized with what we are talking about. So let's look at the first example. Solve the differential equations. So let's look at the first one. So we have dy over dx equal x squared plus 1. So that means you can see that the right hand side is a function of the independent variable. So it's a function of the independent variable. So that means we can simply integrate both sides. So integrating both sides, so integrating with respect to x, what happened? So we have dy over dx on this side, and then dx equal integral of x squared plus 1 dx. So if you think backward, and you can see, so you start with the function and take the derivative, and then now you integrate. So that means you should get the function back. So that means this side is simply going to be y. On the other side, just use the power rule. From the table, you can see in the first line, you see those power rules. So by the power rule, so what's the power rule? We know that if you have x to the n, if you integrate that, what you're gonna get is x, you add 1 and divided by the same number plus c. This is what we normally call the power rule. So from the power rule, and this actually when n not equal to -1, because if n equal to -1, you have a special case 1 over x dx, and you can see in this case you're going to get simply natural log absolute value x plus c. So those are two different cases what we have. So according to the power rule, you're going to get x cube over 3 plus 1. 1 means x to the 0. So that means we can still use the power rule. So you're going to get x to the 1. That means x over 1. That means 1. plus a constant. So that's the answer for the first differential equation. You can see it's so simple. And you may wonder why I did not write two constants for the two sides. Actually, you can do that. So if you want, you can write two constants. So that means here you will see that, so you will get a one constant to this side. You can say plus C1, and you will get another constant to the other side, C2. But what will happen is you can always bring that constant to the other side. And then so you can probably see in this case, C is simply given by C2 minus C1. That's just another constant. So because of that, we are not going to add two constants to both sides. We only add a constant to one side. But if you want, you can do that. You can add two constants and then at the end bring them to one side and write C2 minus C1, and the C2 minus C1 you can call C finally, just to write like that. So but in the future we only write a constant to one side only. Okay, so let's look at the next one. Let's look at the next one. So we have dy over dx equal sine x minus e to the 3x. So again, as before, you can see the right side is just a function of the independent variable, so you can directly integrate. So integrating with respect to x. So we integrate with respect to x, and you can see, so you want to think about where the sine x coming from, and you can see that sine x is, if you think backward, and you know that the derivative of the cosine function. Derivative of the cosine function is negative sine x. So that means you have to manipulate the negative sign. And then also we know that the derivative of e to the kx, if you have a constant k, and the derivative is simply k e to the kx. So we can use these two facts here. That means if you integrate, it will be backward. So if you integrate, what will happen is you can write this as uh, on the left side you get y, on the right side, because this is a sine x, so you should end up getting sine x. So that means you should have start with not the cosine. If you start with cosine, you should get negative sine. Since this is sine alone, you should start with negative cosine. Negative cosine. So then what will happen is that negative sign get cancelled out. So that's take care of the first term. For the second term, you can see there's a k. So when you take the derivative, you get the k out. So to cancel that k, what you do when you integrate, you divide by k. So that means it's going to be e to the 3x divided by 3. So then why we do that? Then you can see when you take the derivative, there's a 3 coming out. That 3 can cancel out with the 3 in the denominator. And then don't forget the c. We add only c to one side, because as we discussed in the previous example, you get two c's, c1, c2, but you can always bring that to one side. So we just write one c in this case. So that's the solution for this problem. So let's look at the next one. So as the next one, we have dy over dt. Now it's a new variable, t times t minus 1. First we notice that this side is a function of the independent variable. So it's a function of the independent variable, in this case t. But there's a product, and unfortunately we know that there's no product rule when you take the integrals. So that means we need to distribute first. So what you do again as before, integrating with respect to t now. So integrating with respect to t, we have integral dy over dt times dt on this side. The other side is again t minus 1, and we know that there are no product rule. That means what you need to do is we can distribute. So we can write this one as t squared minus t on the right side, and then you can see now we can directly use the power rule. So the left side is simply going to be y. On the other side, if you use the power rule, you get t3 over 3 minus t squared over 2 plus c. So that is the answer to this problem. So you can see it's very easy. Only thing that we need to understand is you cannot do a product, you need to distribute that. Okay, so let's look at the next one. So as the next one, we have dy over dx equals secant x plus tan x plus 1 over x. And clearly the right side is a function of the independent variable, the function of the um, independent variable, function of the independent variable. But here you may see some unfamiliar functions, and you can see these functions you can find in the table, and also this is something like you learn in Calc 2. So we know the derivative of the integral of the secant is natural log secant tan, secant plus tan, and the integral of the tangent is the natural log secant x. And so directly from the table, and you can find these answers like this. So again we integrate with respect to x now. So integrating with respect to x, on the left side you get y, and then what we have here is the integral of secant x dx plus the integral of tan x dx plus the integral of 1 of x. So we do term by term, and secant, we know that's the natural log secant x plus tan x, and if you are not familiar with this, then you can look at the table. So secant x plus tan x, and the next one, actually you can see why we have a different special formula, because we know the answer is natural log secant. The reason is you can write tan as sine over cosine, sine over cosine, and then we know that the derivative of cosine is negative sign. So what we do is we put a negative sign outside and we put a negative sign inside, and we write it like that. And then you can see this is, you can see the top is the derivative of the bottom function. So we know the special formula under 4 formula trick, because it's going to go like that. So it's a bottom, the top is the bottom of the derivative of the bottom function. So if that is the case, then you know that the answer is, if you take the integral, it is simply going to be the natural log of the bottom function, and that's the same argument we use here. So because of that, you can write this one as negative, you can say this is negative natural log of the bottom function, we can write it like that first, plus this is ln x, 1 of x we know that's ln x, so it's a ln absolute x, that's a formula, you can also find that there. And then you can also do something here, you can move this negative sign inside as a power, so that means the cosine going to be secant. So you finally you can write this one as ln secant x plus tan x, and then plus you can write this one as ln secant x, and then plus ln x plus c. And if you want, you can combine all of them into one, you can do that too. So if you combine them into one, you can write this one as, or you multiply everything, so it's going to be x secant squared x, and then plus x secant x tan x. So you can write it like that, plus c. So you can write it like that. Yeah, so let's look at the next one. So as the next one, we have dy over dx equal 1 plus ey. And you see a major difference here, and you will see that the right side is not a function of the independent variable, is a function of the dependent variable. So it's a function of the dependent variable. So that means we cannot use the argument that we used before. So that means we cannot. So cannot integrate with respect to x. With respect to x. X is the independent variable with respect to x. So that means we need a new technique. So let's talk about the second type. So I'm going to call this the type 2. So let's talk about type 2 now. So in type 2, what we have is, we have dy over dx is a function of the dependent variable. So gy is a function of the dependent variable. Function of the dependent variable. So that means what we're going to do is, we're going to move the same variable to the same side, or we do like interesting argument here. What we do, we flip the equation. We flip the equation. So flip the equation. So when you flip the equation, what will happen? You can bring this to type 1. So when you flip, you can say dx over dy, and then on the other side, what will happen is 1 over gy. So when you flip that, this is what happened. And then now you can see this again type 1. So this simply become a type 1 problem, type 1 with the assuming the independent variable is y now. That's how we do. So just do the same thing as you did before. So we assume y as the independent variable and integrate with respect to y. So assuming y as the independent variable, so you can integrate with respect to y as type 1. So that means you integrate dx over dy with respect to y now. Same thing on the other side, you integrate this one with respect to y. So this can leads to the solution. On the left side, now what you get is you get a function x as a function of y now. You can just write x here, but it's a function of y. On the other side, we're gonna integrate this. So it's a gy dy. So that's you can use as a formula for type 2. And then also what we do, if possible, we try to solve for y. So if possible, solve for y. If possible, solve for y. But sometimes we cannot do that. So let's look at a few examples and see how things gonna go. Also, let's look at another argument that you're gonna learn later, what we call the separation of variable method. In this method, actually, rather than flipping the equation, we say we're gonna move the terms to the y terms to y side, x terms to x side. So that's like another argument that we can do. So another way to see this is to move gy term to the dy side. So just so then same variable in the same side. So for example, so we have dy over dx, which is equal to gy. So what we do, we can divide by gy, assuming gy is not equal to 0. So you can write this one as 1 over gy dy equal, we move dx to the other side. Now what we do, we integrate two sides separately. So that's like another argument, and you can see that you get the same answer as before, but this is like another argument to how you do that. So rather than flipping the equation. So let's look at several examples and see how things gonna go. So let's look at the first one. So as the first example, we have dy over dx equal y plus 1. So the first step is we flip the equation. So we can write this one as dx over dy equal 1 over y plus 1. So now this is type 1. So this is type 1. So that means we can integrate the two sides with respect to the independent variable or what is in the bottom. So integrating with respect to y, we get x on this side, and then on the other side integral of 1 over y plus 1 dx dy, and you can see this is just the natural log, because we know that the derivative of natural log y plus 1 is 1 over y plus 1. So because of that, if you think backward, this is simply going to be y plus. You don't need substitution for this one. Just think backward. How you get 1 over y plus 1? What derivative of that? So you see that is a derivative of ln y plus 1. So that's like a best way to think problems like this. And we had a C1 here for a reason. So now you can see this is an implicit equation. So this is implicit equation. So what you do, if possible, we try to solve for y. Most of the time we can actually. Let's see how we can solve that. So solve for y, that's how we do. Solve for y. So first I'm going to write this equation like flip the sides and write it like this. Just flip the equation. And then I'm going to move the C1 to the other side. So you can write this one as ln y plus 1 equal x minus c1. And then after that we know from algebra, if you have a log equation, you can write this one as a exponential equation. So what will happen when you remove the log, what will happen, you get the base. In this case the base is e, base is in natural log means base is e. So that means we can write this one as the absolute value y plus 1 equal e to the function whatever in the other side. So write it like that. And then we again use some algebra. We can write this one as, we know that when we have a power, you can write this as a product. So you can write this one as e to the, I'm going to write the e to the c term first. So e to the negative c1 times e to the x. So you can write it like that because there's a sum. So sum becomes a product from algebra. Now the next step is I'm going to remove the absolute sign. When you remove the absolute sign, when you write y plus 1, what will happen is you get plus or minus. You get two terms because we don't know, because when you take the absolute sign, we don't know whether it was a plus or a minus. Since we don't know, so it may be plus or minus. So we write it like that, e to the negative c1 e to the x. Now what we do, just to make the algebra simple, this whole expression I'm going to give like a different letter. So you can just call this whole expression just a c, some letter. So if you do that, then you can see, then you can solve for y. So if you solve for y, you will see that you get y equal c e to the x, and then when you subtract 1 minus 1. So that is the final answer for this problem. So you can see how all the algebra are going to work and what happened when you take the absolute sign out. So things like that. Okay, so that's how you solve the problem. So let's look at the next one. Now you can see that this is of type 2 because the function is a function of the dependent variable. So what we're gonna move and integrate. So rewriting and integrating, we have dy over y squared plus 1 equal dx. Now what you're gonna do, you're gonna integrate the two sides separately, and then we know these formulas from calc 1. So we know that the dx over 1 plus x squared, the integral of 1 plus x squared is simply tan inverse x plus c. And if you look at the general case, you get dx over x squared plus a squared, which is equal to 1 over a tan inverse x over a plus c. Sometimes we also write this one as arctan. So some people write this arctan x. So it's the same thing. Plus c. Okay. So because of that, this side is simply going to be tan inverse y. On the other side is this going to be x plus c. So if you take the tan of both sides, you can write this one as y equal tan x plus c. So that's what you get. So let's look at the next problem. So as the next one, we have dy over dx equal y3 minus y cube minus y. And you can see this is type 2. And then also we notice that if you factor this y, you can see that you can write this one as y squared minus 1. And if you look at the complete factorization, this is y minus 1 and y plus 1. So that means this is going to give you 3 constant solutions. So the constant solutions are the constant solutions. Constant solutions are, you can see y equals 0 and then y equal plus or minus 1, because all those 3 solutions are going to satisfy this equation. So assume that is not the case. Assume y not equal to any of those constants. So then what we can do is, then this is simply type 2. So we're going to divide by both sides by that. So you can write this one as y3 minus y, and the other side you get dx. And then you know that the best way to do this is use the question is how to integrate the left side. So we can use the partial fraction method. So to integrate something like this, we can use the partial fractions method, or sometimes we call the uh, PF method, PFM. Um, yeah, so to do that, what we're going to do is we're going to write the complete factorization first. So we can write this one as dy over, if you look at the complete factorization, which is y times y minus 1 y plus 1. And then what we can do, we can write the on the other side, so you simply get x plus c, so that plus is done. For this one, what we're going to do is we're going to find the partial fractions. We try to find the partial fractions for this one. To do that, so write in the partial fractions. So we write the partial fractions, so it's going to be 1 over y, y minus 1, y plus 1. So this is like an easy case. So we write identical, so 3 lines, not 2 lines, 3 lines identical. 2, we write 1 by 1. There's no particular order, so let's the first one, and the second one, and the third one. So when these factors are different, when the zeros are different, it is very easy to find ABC, because you can just plug in the values and you can get it. So let's see how it's going to work. So after multiplying, we can write it like this. So this is what you get after you multiply, and then what we can do is substitute, and you can see your goal is to make this term 0, just to make this term 0 and the other term 0. So you try to make two terms 0 at the same time. So what you do, look at the common term. In this one, the common term is y minus 1. That's the common term. That means if you plug in 1, those two terms gonna get cancelled out or simply become 0. So you get b. So that's the idea. You just try to find the other two terms and find what is common, plug in the negative of the common value, because to cancel y minus 1, you plug in 1. So that's the idea. So just keep doing it. And also, if you are not familiar with this one, you can find the link in the description to learn about this one. And also you can, there's another technique called cover up method. I have also put the link for that one. That's also like a quick way to get this one. So it's a cover up method, and I discussed that in the video. So let's use the substitution method here. So we can substitute first y equal 0. If you plug in y equals 0, you can see you're going to get a. If you want to find a, you're going to make the other two terms 0. So you plug in y equals 0. So you get if you plug in y equals 0, you can see 1 equal so the last two terms get 0, so you get a times negative 1 positive 1, and this is going to give you a value, so a is simply going to be negative 1. So you get very straightforward. And then if you plug in y equal 1, and that means if you plug in 1, you can see the first and the last terms are 0, so you get 1 equal b times 1 times 2, so this is going to give you the b value, which is 1/2. And if you plug in y equal negative 1, you can see 1 equal the first two terms going to be 0, so you get c times negative 1 negative 2, so this is going to give you c equal 1/2 again. So those are the three values that you get. So now we're going to plug in that, and we can integrate. So we can write 1 integral of negative 1 over y equal negative 1, and then 1/2 over y minus 1, and again 1/2 over y plus 1. So that's what you get, dy equal x plus c on the other side. Now we can very easy to integrate. So this is negative ln absolute value y, and the 1/2 ln y minus 1, and then this again 1/2 ln y plus 1 equal x plus c. So what you can do now is you can multiply by 2, and combine terms. So this is okay, perfectly fine, this one. But what we can do is we can see whether we can simplify this a little bit further. So let's do that quickly. So we're going to multiply by 2 and combine. So multiply by 2 and combining, we have this. So you get ln, we have a y minus 1, y plus 1, and the negative, you can write it in the denominator. So you can write y squared, and on the other side you get 2x plus 2c. So the numerator, you can write this as y squared minus 1 over y squared. On the other side you have 2x plus 2c. And also you can see, you can simplify this further. You can write this one as by dividing 1 minus 1 over y squared. You can write it like that. You get 2x plus 2c. So now we can write the exponential form. Okay, writing the exponential form, you can write this one as 1 minus 1 over y squared. And also I'm going to do few things at the same time. So so you get e to the 2x times e to the 2c, and also when you remove the absolute sign you get plus or minus. So I did all of them at the same time. And then what you can do now is we can combine these two and just say c or a. So we can write this one as a e to the 2x. So where a is simply plus or minus e to the 2c. I just call that a just to make it easy. Okay, now what we do, we can again switch terms around. So we can write this one as 1 over y squared equal, and you can move a terms this side, y to the other side. So you can write this one as 1 minus a e 2x, and then you can flip over this one. So when you flip over, you get y squared equal 1 over 1 minus a e 2x. Now finally what we can do is we can take the square root. So when you take the square root, you get y equal 1 over, actually you can write the plus or minus in front. So let's write plus or minus 1 over 1 minus a e 2x square root as the final answer. And how do you know a? So you find a using initial conditions. So you're going to find a using initial conditions. So it can tell you which sign to pick, whether it's a plus sign or minus sign. So that's how you solve the problem. Just to complete all the different types, I'm going to do one more trigonometric problem. So let's do that as the last one, trigonometric problem. So as the last one, let's try to solve this problem. dy over dt equal tan y plus secant y along with the initial condition y0 equal pi over 2. So and then clearly this is type 2. So what we do, we're going to divide. So we can write this one as 1 over tan y plus secant y dy equal, the other side is simply dt. Now how to solve this problem? And you can see that you need to multiply by the conjugate. So we multiply by conjugate, you get this. So before you use the conjugate, and you can see that I have switched the terms. You will see why in the next line. So now you can see the bottom simply going to be because of the difference of squares formula. So you're going to get this one now. So you get that, you get secant y minus tan y over secant squared y minus tan squared, and you can see the bottom is simply equals to 1 using the Pythagorean identity. So that means you simply get, so you get integral of secant y minus tan y dy equal t plus c. Now using the table, common value table that you can find the description, you can get that the integral of secant is natural log secant plus tan, so the secant y plus tan y, and minus the integral of tan is the natural log of secant y equal t plus c. So now what we can do, we can combine them into one. So we can write this one as ln. So you write the first one, secant y plus tan y, and the minus means a divide. So we divide by secant y equal t plus c. So we can use some of the algebra trigonometry now. So you can see, you can multiply the top and bottom by cosine y. When you do that, the secant and cosine, the product is 1. So you're going to simplify like this. So if you multiply the top, and you can see this is simply going to be 1 plus sine y, the top. And the bottom is simply going to be 1. So this is t plus c. So you can see it simplifies very well. Now what we're going to do is we're going to use the exponential form to rewrite this like this. So we can write this one as 1 plus sine y equals to plus or minus, and you can see this is e to the t, e to the c, and then as we discussed before, you can write this one as a e t, where a is equal to plus or minus e to the c. Okay, now we can solve for y. So sine y, so you can write this one as sine y equal a e t minus 1. So that is the implicit form of the solution. That's the implicit solution. Okay, so this is the implicit solution of y. So now what we can do is we can use a condition. So let's use the condition. So using y0 equal pi over 2, so you can see that you're going to get sine pi over 2 equal a e0 minus 1, and this is equal to a minus 1, and then we know that the sine pi over 2 equals to 1, so this says that a is equals to 2. So that means you get the solution in the implicit form, sine y equal to e t minus 1. Let's also try to find the largest possible interval of t for this problem. And to find the largest possible interval, what we know is that we know the sign is always in between 1 and negative 1. So we can write it like that. So 2et minus 1 has to be between 1 and negative 1. Now what we can do, we can add a 1 to every side, all three sides. So if you add a 1, you get 0 on this side. So you get 2et and then less than or equal 2. Now what we can do is we can divide this equation by 2. So you can write this one as 0, et less than or equal 1. And the first inequality is always correct. So what we do is to find the next one, we take the natural log. So if we take the natural log, so taking ln of this inequality, so what will happen is we know that it's a 0. So at the limit, you can see that you get negative infinity on this side. That's when the ln 0 goes negative infinity. On the other one is you can see that ln et means t. Actually, there's a very strong inequality here. So it's going to be t. On the other side is so you're going to get 0 on this one because we know the ln 1 is 0. So that's going to give you the largest possible interval. That means the t has to be in between negative infinity and 0. So that's how you solve the problem with the initial largest value of the t. So it's a good exercise that see whether you can try to find the y explicitly. See whether you can find y explicitly for this problem. It can be a little challenging, but see whether you can do that. And you can see the answer in the description. Okay, thank you so much for watching.